In the last video, we have been discussing this example where we've been starting out with a type that we wanted to define a function of type int to int, pairs of two integers, and then we've been generalizing the type first to a pair of two a's, and ultimately to a pair of ab going to a pair of ba. And we had seen that just by doing this, we restrict the amount of possible functions that we can write of these types from virtually infinite to 4 for this one, and ultimately to 1 for this one. So what are the consequences of this phenomenon that parametric polymorphism so severely restricts the ways in which we can implement functions? Right. As I said before, it generally is a good thing. It provides you with guidance as a programmer. If you have determined that a type is supposed to not matter, right, then the type system subsequently actually prevents you from making any kind of assumptions about this type. And that rules out going off in all sorts of wrong directions while you're implementing the function. It also provides information to the user again, right? Not just does it give the user the choice how to instantiate these types, you also know that the behavior of the function cannot in any way depend on how you make this choice, that the function cannot look at the nature of polymorphic values, that there are no specific operations that are available to the implementation. So, and that means, like, if you think about it a bit more, that just by looking at a polymorphic type, one can often obtain non-trivial properties of the functions. One can essentially derive theorems, or at least partial theorems, about how the function behaves, and this is sometimes called parametricity. So, for example, in an extreme case, in this final example, right, just by looking at the type of the function, we can know that this must be the function that swaps the components of the pair, if we assume that it is total, at least, right, that it does not crash. But then we know exactly which function this is. So as a slightly more realistic example, let us look at the type of the map function. I've written the map function on lists down once more here in this module. And this is our type signature, A to B to list of A to list of B. And we see that it makes substantial use of parametric polymorphism. And let's look at it not actually so much through the lens of wanting to implement the map function, but just what kind of information does the type signature give us here? And it actually gives us quite a bit, right? We have this function that goes from A to B as an input, and we have a list of A's as an input, but we have to produce a list of B's as an output. So this list of B's has to contain elements of type B. And that is a type that we, as the implementer of the function, we don't know anything about. And in fact, the only way that we have available to create B's can come from our inputs, right? And if we look at our inputs, the only way we have, in concrete terms, to produce a B is this function that we are given, right? That is the only thing among our inputs that mentions a B, but it tells us that in order to produce a B, we have to have an A, right? And again, we don't know anything about the type A. It's something that the caller of the map function can choose. The only A's we have available come from this list that is also among our inputs. So what we know just by looking at this type is, and that is actually quite a lot, that all the lists that it produces must result from applying the given function to elements of the list that we feed in. And this has a number of consequences. In particular, it means that in the case of the empty list, right, if the list of A's is empty, then we don't have any A's to start with. So there is no A that we could possibly apply our function f to, and that means that there is no way to produce any legal value of type B, and that means that the function must return the empty list. There is no other choice. Right? In this case, we are completely constrained as well. We have no other choice. Right? In the cons case, we do have other choices. So the map function is not uniquely determined by this type, because look, we could always just return the empty list. That would be fine. Right? That's perfectly fine. Or we could suddenly start to flip the order of elements, right, and not generate them in the same order as in the original list. Or we could like always produce 2 copies of f of x, right? That would be fine as well. But we still know that whatever we put into this result list must be an application of f. And it must be an application of f to an element that comes from the original list. Right? And that for the user of the function, again, also has consequences. Right? If the user sees a function of this type, even without looking at the implementation, well, they know that if they feed in the empty list, they will get the empty list back. But it also means certain things about if they feed in certain lists or certain functions. So, for example, if you consider something like map and then as function you're using ×2, something that doubles its argument. Now you know by means of properties of the function that doubles its element, that multiplies by 2, if you consider integers as a starting point, that the result of multiplying by 2 is an even number, is always an even number, right? And that in turn means that because all the elements in the resulting list must be applications of this function, right, even without looking at the implementation, even without knowing what map exactly does, just by looking at the type signature, we can determine in such a case that the resulting list, if it contains any numbers, it must contain even numbers. So there are interesting properties that can be derived about functions just from looking at their type signature. This feature of the type system is sometimes called parametricity. And there are papers and other tutorials about how one can take a type signature and derive these theorems. There are even online tools that can be used where you can type in a type signature and it gives you theorems about functions that have this type signature. But a more practical, there is an intuition that you can build as a programmer, that you can really rely on these kinds of properties, that you can like both let yourself be helped as a programmer to go in the right way, but also as a user, if you see a polymorphic type signature, you can start trusting it. Right? So all this, quite importantly, depends on the fact that you do not have any additional constraints on these types. As soon as you put in class constraints, you're effectively adding extra function arguments, as we shall see in a moment. We'll talk about class constraints next. And that gives you usually significantly more options than you have right now at this point. Okay, so the next part, the next thing we'll do is we're going to look a little bit more at overloading and at classes, and we'll see how that relates to the notion of parametric polymorphism. There is one more thing I would like to discuss before we go there, and that is once again this general tension between, like, do the presence of type variables, do they give you a choice or do they limit you? And I'm going to discuss a small example in the next video about this.